So in the last section we studied ways to approximate solutions to differential equations. In this section we're going to look at our first type of method for directly finding solutions to differential equations. We're going to look at the method of solving separable differential equations. So separable differential equations comes in this form, where the derivative of y is equal to some function of f of x, could be something crazy, directly multiplied to a function g of y. Okay, so if you can separate so that's just an x or a bunch of x's all in parentheses times a bunch of y's all in parentheses, then you can solve using the method of separation of variables. So I've got an example down here. This one meets the criteria because this is like our f of x and this is like our g of y. Okay, so we're going to first start by rewriting y prime with something we studied at the beginning of calculus. Y prime is the derivative of y with respect to, whatever our variable is, x in this case. Okay, and the next step is where we're going to try to get our variables separated onto different sides of the equation. So it's like we're multiplying d of x to both sides of the equation, okay? That makes students feel like we're taking a balanced step, right? You can kind of multiply that dx to both sides. That way, the right side of the equation is with respect to x. And then you probably will be able to guess what we're going to do next. We're going to try to get y over on this side of the equation, except y has to be divided, right? To get rid of it on this side. So we can put a little 1 in front of that dy, okay? So now the left side of the equation is 1 over 2y minus 1 dy. That equals, we got x on this side, right? 2x plus 3 dx. So now is where all the things that you studied at the beginning of this class are going to come into handy. Just remember, there's lots of tricks in our tool belt for integration, okay? So you want to integrate both sides, evaluate the indefinite integral of both sides, that way we keep it balanced. And remember, when you're trying to evaluate the indefinite integral for something for 1 over x, we want to be thinking a natural logarithm, right? Except this one's going to be a little bit trickier, because if we just said that the indefinite integral of 1 over 2y minus 1 was natural log 2y minus 1, we'd be close. But think about when you take this derivative with respect of y of natural log 2y minus 1, that's going to be 1 over 2y minus 1 times 2 because of the chain rule. So I got to put a little 2 underneath here to balance that out. And I think now we have plus our constant c. We'll just call that c sub 1. I think we got it now. If you take the derivative with respect to y, natural log 2y minus 1 gives you 1 over 2y minus 1 times 2. Yeah, so that 1, you could say this is 1/2 too if you don't like that, divide by 2. Okay, so we evaluate the indefinite integral for the left side. For the right side, it's a little bit more clear cut. X squared plus 3x plus some different constant c, right? And then our goal is to try to get y by itself. So now it's kind of like it's back to pre-calculus or our algebra course. We want to get y by itself, so we got to get it outside of that natural logarithm. There's got to be a better way to erase. I just don't know what it is yet. Okay. First of all, we can collect the arbitrary constants. Let's change that. I don't like that. Divide by 2. Let's say that's 1/2 natural log 2y minus 1 equals x squared plus 3x plus just some arbitrary constant c, right? Because if you subtract c1 from both sides, c2 minus c1, that's still some arbitrary constant. And I'm trying to get y by itself, so let's get rid of that 2. We'll multiply both sides by 2. So it gives us 2x squared plus 6x plus c, because 2 times an arbitrary constant c is still some arbitrary constant c, right? And now trying to get y by itself, we've got to we got to have e to the power of natural log 2y minus 1. And we'll do the same to the other side. And then e to the natural log. Those are going to undo each other. That's the whole reason we did it, right? Oh, here, actually, this is plus c up here. So we do that, and it's like, we'll keep that like that. Let's work on that at the end. Sorry, I dropped my c down here. Okay, plus arbitrary constant c up there for right now. Okay. Still trying to get y by itself, so add 1 to both sides. And then divide both sides by 2, or multiply both sides by 1/2, right? So I add that 1/2 to both sides. We got 1/2 e to the 2x squared plus 6x. And then if we say times some e to the constant c, this needs to be 1/2 because we multiply both sides by 1/2. We've got the solution. I'm just thinking this is it right here. Before I move that constant, let's keep that like this. I think there's a different way that books and everything prefer us to write it. This is our solution. If you take the derivative of this, it should be a solution to our original differential equation. You should be able to plug in y prime in here. And if you plug in y in here, you should get a true statement. Sorry, there's one extra bit we can do here to make this look cleaner. This is the solution, but if you rewrite so this arbitrary constant c I was playing around with, multiply that e to the power of c. Right, so this is still the same thing as this term, because if you multiply two things with the same base, their exponents add together, right? But we rewrite it like that because of the fact that c is just some arbitrary constant. So e to the power of an arbitrary constant, that's just c. So this is like times c out here. So you can make things a little bit cleaner if you factor out a 1/2 from everything. And then we have this arbitrary constant c that we'll just write out front. Okay, so that's a cleaner version of our solution, and that's probably what homework software is going to be looking for.